In 2013, a speedrunner was playing Super Mario 64 when suddenly Mario teleported across the level, saving the speedrunner precious seconds. To this day, there has been no known explanation for this glitch, even after a $1,000 bounty was placed on whoever could replicate it. Now, the best explanation is a cosmic ray from space that struck the console's memory, flipping a single bit and altering the game's code in real time. This phenomenon, although rare, is called single event upset, or SEUs for short. It happens when high energy particles such as cosmic rays or neutrons strikes a semiconductor chip, flipping a 0 to a 1 or 1 to a 0 or vice versa. Now, this type of error doesn't cause any permanent damage. However, it can cause unpredictable behavior in computer systems, from gaming consoles to satellites. Now, you may be thinking, okay, this is just some weird gaming fluke, and why does this matter? However, SUs have caused far more serious problems. They've interfered with flight control systems, they've altered elections, they've even impacted cloud computing services. And as our technology shrinks and becomes more advanced, it's making it, the likelihood of SUs is increasing, making it a growing concern for engineers and researchers alike. In this talk, I'll dive into how SUs happen, the real-world consequences, and what scientists are doing to prevent them. Now we know what SUs are and how they happen. Now that we know what SUs are, let's break down the science behind them. How do SUs flip bits in your computer? At the core of this issue is something known as high-energy particle interaction. Cosmic rays, or particles traveling at nearly the speed of light, are constantly bombarding Earth. Most of these are absorbed by Earth's atmosphere. However, some make it through, creating secondary particles such as neutrons. When one of these particles strikes a semiconductor chip, it can disrupt the electrical charge stored within a memory cell, flipping a single bit from a 1 to a 0 or vice versa. Now, this seemingly tiny change can have massive consequences depending on what that bit controls. To put it simply, imagine your computer is a massive spreadsheet filled with ones and zeros. If a cosmic ray just changes one of those values, your system might miscalculate, crash, or behave unpredictably. In most cases, single event upsets go unnoticed. However, they can trigger anything from a simple glitch to a system-wide failure. So where do SUs happen most often? Well, the answer depends on how much radiation exposure a system is exposed to. Space is the worst environment. Without Earth's atmosphere to protect them, satellites, space probes, and the International Space Station are constantly bombarded by cosmic radiation. NASA and SpaceX specifically designed their spacecraft with extra shielding and error correction methods to prevent from single event upsets. High altitude flights are also more at risk. Commercial airplanes fly at around 35,000 feet, where cosmic radiation is significantly stronger than at sea level. In fact, airline computers and even passengers' personal devices are more likely to experience single event upsets at cruising altitude. Now, SUs don't just happen at high altitude or in space, they can also happen at sea level. Atmospheric neutrons can also cause bit flips, especially in high-density electronics such as cell towers, data centers, and even personal devices. Even your laptop and cell phone are not completely immune. With technology shrinking to the nanometer scale, modern processors and memory are becoming more vulnerable to these tiny disturbances. And as we rely more on AI, cloud computing, and autonomous systems, the need to understand and mitigate these issues is becoming all the more paramount. Now that we understand what SUs are, how they happen, let's look at some real-world consequences where a single bit error has led to some serious problems. One of the most alarming incidents happened on Qantas Flight 72 in 2008. The Airbus A330, cruising at 37,000 feet, suddenly experienced a series of violent, uncommanded dives, injuring passengers and crew members alike. Investigators traced the issue to the aircraft's flight control system, where a single event upset caused a faulty data reading, leading to the computer to inaccurately detect dangerous air conditions. As a result, autopilot disengaged and the plane abruptly pitched downward. Fortunately, pilots were able to regain control and safely land the plane without any casualties. However, this incident highlights how SUs can affect even highly redundant aviation systems. SUs have even affected elections. In 2003, a Belgian candidate received 4,096 extra votes due to a single bit flip in an electronic voting machine. Fortunately, officials caught the error when they noticed that the total number of votes were higher than the total registered voters. Even Google's data centers have recorded thousands of SUs. In 2009, Google researchers published a paper revealing that cosmic ray-induced bit flips were happening regularly, sometimes leading to data corruption, sometimes just to software glitches. Since then, they've implemented advanced error correction techniques to prevent this. These examples show that SEUs can show that SEUs can affect anything from a video game glitch to interfering with flight control systems. And this raises an important question. How do we protect our systems from SEUs? The good news is that researchers have already come up with several techniques to prevent these. One of the most simplest and easiest is error correcting code memory, or ECC memory. Unlike regular memory, ECC memory can detect and correct single bin errors automatically. This is especially important in mission critical systems such as servers, medical devices, and even spacecraft computers. Many modern data centers implement ECC memory to prevent data corruption from cosmic rays. Another technique is triple modular redundancy. This method involves running 3 identical circuits or processes in parallel. Each one of these performs the same computation, and the system compares the results. If one of the 3 results are different, likely due to an SEU, the system will ignore it and instead use a majority vote to determine the correct result. Now, this approach is often used in aerospace and military applications, where reliability is absolutely paramount. For systems operating in extreme environments, engineers use radiation-hardened electronics. These components are specifically designed to withstand high energy particle exposure. NASA and SpaceX use these kind of chips in their spacecraft to ensure that they do not suffer from single event upsets while operating beyond Earth's protective atmosphere. However, radiation-enhanced electronics are expensive and slower than commercial processes, and so they're only used when necessary. Finally, we have software-based methods, such as memory scoping. This is where software periodically scans memory for errors and corrects them before they can cause any issues. Redundancy checks, such as duplicating calculations and cross-checking data, are also common in safety-critical applications, such as finance and aviation. Even cloud providers like Google and Amazon implement software-level error correction to maintain their system integrity. These mitigation strategies ensure that SEUs remain a rare inconvenience rather than major disasters. Now let's take a closer look at why this problem is becoming more important in modern computing. Today's processors and memory are built at the nanometer scale, meaning that a tiny disruption from a cosmic ray has a significantly larger impact than in older, larger circuits. To combat this, researchers are looking into machine learning and AI to predict and correct single event upsets in real time. By analyzing patterns in data corruption, AI systems can detect anomalies and correct them before they can cause any real damage. Another emerging field is radiation-aware computing. As AI, quantum computing, and autonomous systems are becoming more critical, engineers are designing software and hardware that can withstand radiation exposure. As mentioned, this is especially important in fields such as spaceflight, high-altitude flights, and medical devices such as pacemakers. While we may never fully eliminate the threat of SEUs, research is ensuring that our technology remains reliable, even in the face of cosmic interference. Thank you. Does anybody have any questions?